Titration. In this technique, a known concentration of a base or an acid is slowly added to a solution of an acid or base. So in this burette, where we can measure the volume accurately, is the known concentration of the solution. So if we know the volume that we add to our beaker of the acid and we know the concentration, we can calculate the moles. Here we are going to have a known volume. Okay, so this is a known concentration and a known volume at the equivalence point, or I should say at the end point, depending on which one we're doing. All right, this is a known volume, usually an unknown concentration. We know at the equivalence point the moles of acid is equal to the moles of base stoichiometrically, meaning the moles of hydronium is equal to the moles of hydroxide. Okay. So a pH meter or indicators are used to determine when the solution has reached its equivalence point. And that is the point, again, at which the stoichiometric amount of acid equals that of base. What this means really is the moles of hydronium is equal to the moles of hydroxide. The reason why I state it this way is in case we're using a diprotic or a triprotic. This equivalence point is when this happens. Okay, indicators, we have to be careful. The choice of the indicator can make the equivalence point at the point at which the color changes. But as we'll see, we'll have to be careful about that. All right, when we are titrating a strong acid with a strong base, this is the type of curve that we will get. And in this beginning part right here, before we've added any volume of sodium hydroxide, the pH is 1. These examples assume, okay, that we are using concentrations of the acid and base equal to 0.1 molar, that the initial volume of your titrant is 50 milliliters, and that you are dealing with an acid base ratio of 1 to 1. So monoprotic acid and a base. Okay, so in the beginning we have this pH of 1. All I have in the solution at that point before I add any of the base is the strong acid. So I have hydronium and whatever the anion is, in this case hydrochloric. As I start adding base, I'm going to give excess acid and the salt, because remember, acid plus base gives me salt plus water. At the equivalence point, the moles of acid is equal to the moles of base, hydronium to hydroxide. The solution only contains water and the salt from the cation. The salt from the cation of the base and the anion from the acid. So in this case, because it was hydrochloric, strong acid, and sodium hydroxide, all I have at that equivalence point is sodium chloride, salt water. As I continue to add base, I run into excess base, where in the solution I have salt and I have the sodium hydroxide. So the base at this end is due to the excess sodium hydroxide, and we can see a pretty high pH at the end of a titration of a strong acid and a strong base. There are four, by the way, there are four curves that you need to be familiar with and be able to identify. So a titration of a strong acid and strong base, again, the pH initially is pretty low. The equivalence point, meaning the point of where the moles of acid is equal to the moles of base, is at the pH of 7. The pH at the beginning of the curve is due to the excess acid, and at the end is due to the excess base. Okay, that's when I'm titrating a strong acid with a strong base, the strong base being in the burette. It looks a little different when we are titrating a weak acid with a strong base. Okay? It's the conjugate base of this acid that affects the pH as it's formed. So at the very beginning, I have the initial weak acid, okay, slightly higher pH. Throughout this curve, they call this the buffer region, because I really have a buffer mixture of the acid and its salt. And as we've seen, that is the buffer. At the equivalence point, I have the anion of the weak acid, okay, and it causes that pH to be slightly higher than 7. Because remember, if I've got this salt, this CH3COO-, that anion, with water, it is going to set up the equilibrium with the weak acid. So it's going to liberate hydroxide, which drives the pH up at the point where my initial base moles is equal to my initial acid moles. Then we see at the end of the curve, again, because I've got an excess of a strong base, I've got that high pH again. Okay. So again, weak acid with a strong base, the anion, the conjugate acid of that base, affects the pH as it's formed. The pH at the equivalence point is greater than 7. Okay. If you notice, this is where we need to talk about something called the endpoint. The endpoint is when the indicator changes color, and the equivalence point. For this particular titration, you would want to choose this phenolphthalein, because this is the color band and the pH range for the phenolphthalein to change color. It is about the same as the equivalence point. Methyl red color would be a bad choice for an indicator because it starts changing concentration, or I'm sorry, starts changing color at a relatively low pH, pretty different from where that equivalence point is. Okay, so things to remember about the curve for a weak acid with a strong base. The initial pH is higher than for a strong acid. Oops. We have a buffer region prior to the equivalence point. There is a smaller jump in that pH at the equivalence point, and then after the equivalence point, the pH again is due to the excess base. pH at the equivalence point is higher than 7, greater than 7. Interesting thing to note, at half of the equivalence point, so if the equivalence point is at 50 milliliters after base is added at 25, the pH at this point is equal to the pKa of the acid. You should be able to work that out on your own. If not, come in and ask. So you'll see the weaker the acid is, okay, meaning the smaller the Ka, you can see that the changes near the equivalence point get more and more subtle and more difficult to tell with this particular, with a titration. What does a strong acid with a weak base look like? You can see the curve looks more like a strong acid in this part. So the initial pH is relatively very low. The pH is relatively constant through the buffer region. There is a jump in pH, and it flattens out after the equivalence point at a fairly low pH. I urge you to look in the book for perhaps a little bit better picture. Your pH is going to be, at the equivalence point, is going to be less than 7, and that's because of the salt that's present. The salt is going to be the cation of a weak base. That cation is going to attract the hydroxide of the water, freeing up the hydronium, which is going to drive the pH less than 7 at that equivalence point. Hang on a sec. Okay, so if we look at a weak acid and a weak base, what we're looking at is this curve down here. Again, the pH of the starting point is fairly high. The addition of the base causes the pH to rise steadily. The change in pH at that equivalence point is very difficult. It's less sharp. After the equivalence point, the pH flattens out, again at a fairly low pH. This equivalence point is not clearly defined, and it may be better to use other techniques other than titration to actually determine what the equivalence point is. Okay, so strong acid, strong base looks like this. Weak acid, you see the initial pH is higher. The jump of pH right around the equivalence point is less so, and then we finish out with the high pH of that strong base. Hang on a minute. I wanted to move the picture over a little bit so that we could see the y-axis. Strong acid, weak base. You see the strong acid curve in the beginning. A shorter rise because of that weak base not being able to get to the same pH as a strong base would have. And then really combining these two weak sections, you get the titration curve of a weak acid and a weak base. What I wanted to show on this particular curve is we've talked about the titration of acids with base. You can also titrate bases with acids, and you would just kind of get a like an upside down curve. I don't know how to explain it, so I thought a picture would be much better to do so. So here's a weak base, the blue line, with a strong acid. So you can see this weak base curve here, less of a pH jump at the equivalence point, and then the pH at the end where my acid is in excess being looking more like that strong acid curve. This curve in red is going to be the change strong base, strong acid. So the blue one is what you're looking at. And again, the methyl red choice here would be better. Phenolphthalein for a weak acid, weak base, strong acid titration would be a bad choice. Okay. And then just one more curve or a picture of the 4. See if you can identify which is which, and hopefully we can take a look at that in class. Polyprotic acids. These are acids that have more, why is this here? Okay. Polyprotic acids. When one titrates a polyprotic acid with a base, you get an equivalence point for each dissociation. And depending on the acid, you can get a pretty curve like this. Sometimes it's difficult with the polyprotics. Okay. So when you're actually doing the titration calculations, remember Do the stoichiometric calculations first, meaning do the neutralization, determine what is in the solution. If you have excess strong acid, strong base, the pH is going to be due to that strong acid or strong base when they are in excess. If I have a weak acid or a weak base, and I have that acid and its ion, for a weak base it would be the cation, for the weak acid it is going to be its anion, then you must set up the equilibrium calculations, ice table, to determine what the pH of the solution will be. Next screencast we'll be talking about indicators.